Enterprises are moving from siloed databases to a shared source of truth. In this course, you'll learn how to design that trust layer with blockchain. Choosing the right network model, shaping the architecture, and planning a safe, incremental migration from Web 2.0 to Web 3.0. Today, organizations are under pressure to replace fragmented databases with a shared, verifiable record of activity. In the Web 2.0 model, each party maintains its own copy of data, so reconciliation, disputes, and fraud checks are slow and expensive. A Web 3.0 approach introduces a shared ledger. Everyone writes to the same timeline of events, and once something is recorded, it's tamper-evident. That single source of truth lets you reduce intermediaries like clearinghouses and manual auditors. Instead of trusting institutions or spreadsheets, participants rely on cryptographic proofs and protocol rules to automate trust at scale. Before you write a single line of smart contract code, you need rules that everyone trusts. In an enterprise blockchain, that foundation is governance. Think of a consortium network as a joint venture. Multiple organizations share a ledger, but they must first agree who can join, who operates nodes, how upgrades happen, and how disputes are resolved. A written constitution captures these decisions. Some choices are enforced socially through legal agreements, while others are enforced automatically with on-chain voting and auditable records. When governance is clear, inclusive, and accountable, the technology layer can evolve without breaking business trust. When you pick a blockchain network for an enterprise, you're really choosing a balance between openness and control. Public networks like Ethereum mainnet give maximum decentralization, but almost no privacy and limited control over participants or fees. Purely private databases give maximum control and privacy, but you lose the benefits of shared truth and ecosystem innovation. The practical middle ground is a consortium network, a permissioned blockchain where participants are known, identities are verified, and validators are pre-approved. This identity layer makes consensus faster, enables higher throughput, and still delivers a shared tamper-evident ledger across organizations. To design an enterprise blockchain, think in layers. At the bottom, the core blockchain handles the peer-to-peer network, consensus, and the ledger itself. Above that, a scalability and confidentiality layer adds sidechains, state channels, or trusted compute, so you can grow without exposing sensitive data. The next layer enforces the enterprise 3 Ps: permissioning, privacy, and performance controls like org registries and access rules. On top, tooling manages keys, credentials, and wallets. Finally, business applications and analytics consume all this securely. Each layer isolates complexity, yet they work together to deliver a trustworthy, compliant platform. Consensus is how the network agrees on the truth of new transactions. For public chains like Bitcoin, proof of work uses massive computation to win the right to add blocks. It's secure but slow, expensive, and a poor fit for enterprise workloads. Proof of stake improves efficiency by having validators lock up value instead of burning energy, and is worth considering for consortium networks. For most permissioned enterprise systems, though, IBFT or RAF-style consensus is the practical default. They assume known participants, deliver high throughput, and give near-instant finality your business applications can safely rely on. Now let's look at how your blockchain actually connects to the rest of your systems. Think of it like a nervous system. Smart contracts are the brain, but they're not optimized for heavy reading or complex queries. Instead, each important state change emits an event. Event listeners pick up those events and push them into a message bus, which reliably queues and distributes them to off-chain services. Those services update an off-chain database that's tuned for fast queries and reporting. This is CQRS in action. Commands write to the chain, while queries read from the off-chain cache. You keep on-chain data authoritative and secure, while user-facing apps stay fast and responsive. Smart contracts are the engine of your blockchain system, and design patterns keep that engine reliable and upgradable. The factory pattern gives you a contract template that can safely mint many standardized instances like orders or identities without repeating logic. The proxy pattern separates storage from logic, so you can deploy new versions of code while keeping data and addresses stable. A state machine enforces allowed lifecycle steps, such as created, shipped, then delivered, blocking illegal jumps or rollbacks. And never hand-roll basics like access control or token logic. Lean on audited libraries to reduce vulnerabilities and speed delivery. As you open the blockchain network to users and partner systems, you need a controlled entry point. That's the role of the Edge Service Gateway. It sits between the messy public internet and your carefully governed nodes. First, it authenticates every request and applies rate limits so no one can spam or overwhelm the network. Next, it translates familiar web protocols into blockchain-specific calls, hiding low-level details from client apps. Finally, it integrates with a secure key vault. The golden rule: private keys live in hardened services, never inside browsers, mobile apps, or other exposed front ends. In an enterprise blockchain, the chain itself should stay lean. Think of it as storing only the receipts, not the whole warehouse. On-chain, you keep hashes and essential metadata, which act like digital fingerprints. They prove that a specific document or dataset existed and hasn't been tampered with. The heavy content lives off-chain, in systems like IPFS, object stores, or existing databases, where it's cheaper and faster to manage. To add privacy, you can layer in zero-knowledge proofs. They let a party prove a statement is true, such as "I'm compliant" or "I'm solvent," without exposing the underlying data. GDPR forces us to rethink blockchain as privacy by design, not an afterthought. The challenge is balancing four pressures at once: strict regulations, integration with legacy systems, scalability for real workloads, and overall cost. Two patterns help a lot. First, private data collections. Sensitive payloads are shared peer-to-peer only between authorized parties, while a small hash anchors the transaction on-chain. Second, crypto shredding. When a retention period ends, you delete the decryption keys for off-chain data, making it mathematically unrecoverable, yet keeping ledger integrity intact. That's how you stay compliant without sacrificing trust or performance. Strangling the monolith is a migration pattern that trades a risky Big Bang cutover for steady, controlled change. You start with the legacy system fully in charge. Then you introduce new blockchain-enabled modules that shadow existing functionality. They receive the same inputs, but their outputs are monitored rather than trusted outright. Once a module proves itself, you route real traffic to it and retire that slice of the monolith. Over time, more capabilities move onto the consortium network until the old core becomes thin or disappears entirely. This approach reduces downtime, political resistance, and migration surprises. To keep a blockchain network healthy in production, you need a DevOps loop that never stops. On one side is continuous integration and testing. Use frameworks like Truffle or Hardhat to automate builds, run unit and integration tests, and replay edge cases. Add automated security scanning, such as Mythex-style audits, before anything can be deployed. On the other side is continuous monitoring. Track node health, block times, gas costs, and unusual events in real time. Finally, treat block explorers as operational tools. Use them to trace transactions, verify hashes, and spot suspicious behavior before it becomes an incident. By now, you've seen how the trust layer is designed, governed, and integrated. The remaining question is execution. How do you actually make this real in your organization? That usually means addressing four gaps at once. First, skills. Your teams need targeted training on platforms like Hyperledger, Ethereum, or Corda. Second, strategy. You need guidance to define your consortium model and adoption sweet spot. Third, delivery. Experienced architects and developers to implement full-stack Web3 solutions. And finally, talent, a sustainable pipeline of blockchain specialists. When these come together, you're not just experimenting, you're systematically building enterprise-grade trust infrastructure. You've now seen how a trust layer is designed, governed, and integrated, from data strategy and smart contracts to migration and DevOps. The next step is deciding where to apply it first. Start with one high-value process that suffers from reconciliation, disputes, or compliance overhead. Map the consortium, which partners must share a single version of truth, and what rules they'll accept on-chain. Then shape an architecture that balances permissioning, privacy, and performance, and run it in parallel with existing systems. With each iteration, you're not just adding blockchain, you're methodically rebuilding how your ecosystem creates and proves trust.